In this video, we're going to look at titrations of weak acids with strong bases and how to do the calculations associated with them. Up front, there's a couple of assumptions I'm going to make for viewers of this. You understand the basics of equilibria, you understand the definitions for acids and bases, you've used Rice tables, many people call it ice tables, and you understand how to calculate pH and pOH. The problem that we're going to look at is the titration of 15 milliliters of 0.56 molar hypochlorous acid, and we're going to titrate it with 0.25 molar sodium hydroxide. Each calculation we're going to determine the pH, pOH, and concentrations of our acids and conjugate bases. The volumes for the sodium hydroxide that we're going to calculate for during the titration are 0 milliliters of sodium hydroxide added, 12 milliliters, 16.8, 28, 33.6, and 35 millimeters of sodium hydroxide. Let's begin. The first calculation we're going to look at is the concentration and pH of the solution prior to any base being added. So we're going to basically do an weak acid equilibrium. We're going to set up a Rice table using a concentration of acid as our initial. We're going to calculate our equilibrium values, and then we're going to calculate based on those answers our pH and pOH. So our reaction is our hypochlorous acid reacting with water, produce hydronium and hypochlorite ion. So on our Rice table, we have our reaction. Initially, we are going to have 0.560 moles per liter of hypochlorous acid. Nothing's been added, so whatever concentration we started off with, that's the concentration we have right now. The change is hypochlorous acid is going to react with acid. We're going to produce the hydronium ion and the hypochlorite ion. And at equilibrium, we will have 0.560 minus X for our concentration of hypochlorous acid, and X will be our concentrations of our hydronium and hypochlorite ion. The setup of the equation, we would use our Ka value to make the assumption that X is too small to matter, so we're going to essentially have X squared over 0.560. When we solve that, we will get X being 1.3 times 10 to the negative fourth, and that will equal the hydronium ion concentration and the hypochlorite ion concentration. To calculate our pH, we simply take the negative log of that concentration for hydronium, and we get 3.89, and our pOH is 10.11. We find the pOH by simply using the 14 equals pH plus pOH formula to determine that value. So our initial pH for this solution prior to any base being added is going to be 3.89. The addition of base is just going to make that pH rise. And the following calculations are going to show us how we can figure out what that pH is going to be. As we begin to add our base, we are going to start off with excess acid. The amount of acid present in the solution initially is going to be more than the amount of base that we're adding initially. So what we have to do is we have to break our problem down into two parts. We're going to do a neutralization stoichiometry problem, and then we're going to use the results of that in an equilibrium. So we start off by doing our reaction in a net ionic form. We set up a Rice table. Only in this case, we're going to be doing stoichiometry of moles or millimoles. I'm going to use millimoles throughout this video. After we do the reaction in the stoichiometry, we're going to identify what acids and bases that we have remaining. And then we're going to recalculate new concentrations with the new volume that we have. We are adding this base to a known volume of the acid. Because we are changing the total volume of the solution, we need to take that into consideration when we are calculating out the concentrations. We will then use those values, those new concentration values, in a weak acid equilibrium. We're going to set up a Rice table, use as our initial concentrations the values that we got in the first part of the neutralization stoichiometry. We'll then calculate our equilibrium values and then determine what our pH, pOH is based on what those equilibrium values come out to be. Let's look at the reaction between our weak acid and strong base. This reaction goes to completion, or essentially to completion, so we don't have an equilibrium. what we need to do is determine what is our limiting and excess reactants. So we're going to start off with 8.4 millimoles of hypochlorous acid and 3.00 moles of hydroxide ion. This reaction, since it's going to go to completion, will use up the reactant that we have the least amount of. Because the reaction is a 1-to-1 ratio, we will use 3 millimoles of hypochlorous acid, we will use 3 moles of hydroxide, and we will produce 3 millimoles of hypochlorite ion. So at the end of this reaction, we will have 5.40 millimoles of hypochlorous acid, and we will have 3 millimoles of hypochlorite ion. Now, because we have changed the volume, we need to calculate what the concentrations of these compounds and ions are so that we can use them in our next part. So we simply take how many millimoles that we have and we divide it by the total volume of the solution. Because we had 15 milliliters of hypochlorous acid and we added to that 12 milliliters of sodium hydroxide solution, we now have a total volume of 27 milliliters. So we take those millimoles and divide it by 27, and we find our concentration of hypochlorous acid has now dropped down to 0.2 moles per liter, and the hypochlorite ion's concentration will be 0.111. These values then will be used in our equilibrium equation. So our initial value for our concentration of hypochlorous acid is going to be 0.200. Hydronium ion, since we're making the assumption that the reaction has not taken place, is 0, and our starting value for hypochlorite ion is 0.111. As the reaction takes place to come to equilibrium, we will drop our concentration, or minus X, for our hypochlorous acid. We will increase our value for the hydronium ion, and we will increase our value for the hypochlorite ion. At equilibrium, these would be our concentration values. To solve these, we plug into our equilibrium expression for our acid. And again, we are going to make the assumption that plus X and minus X are too small to matter. Because this is a very weak acid, that's going to be a safe assumption. So our equation becomes simply our Ka value is approximately equal to 0.111x divided by 0.2. That gives us X as a value of 5.2 times 10 to the negative 8th, which is our concentration for our hydronium ion. Now, because X is too small to really matter, the concentration of our hypochlorite ion is still going to be 0.111. Notice that if we were to add the 5.2 times 10 to the negative 8th based on significant digits, it's not going to affect the concentration. pH is determined based on the hydronium ion concentration is now 7.28, and we can calculate the pOH by simply using the 14 equals pH plus pOH. If we continue to add our sodium hydroxide, we are eventually going to reach a special point in our titration of a weak acid with strong base, and that is the half equivalence. The process that we would use to do our calculations here are essentially the same. We're going to look at our reaction, assume that it is going to go to completion. We're going to set up a rice table and do the calculations in millimoles. And then we're going to use those values and recognize the fact that we are going to have half of the amount of acid that we begin with. And we will see that the ending values for our acid and its conjugate base will be equal. And that's what makes the half equivalence point special. Our weak acid equilibrium we can do several ways, but one of the things to recognize is that at this half equivalence point, the pH of the solution will equal the pKa value, and we will see why that's true here mathematically. Any calculations then can be done using that, or you could go through and do the equilibrium equation and determine your concentrations and pH values just as we did in the previous example. So again, we have our weak acid strong base reaction. Our initial values are going to be 8.40 millimoles for a hypochlorous acid. The amount of hydroxide ions has increased because we have added more volume. The value for our hydroxide is now 4.2 millimoles. Again, we have none of the hypochlorite ion. The value for the change in concentration is equal to 1/2 of the beginning value for the hypochlorous acid. And at the end, we end up with equal values for the millimoles of our hypochlorous acid and hypochlorite ion. Again, we have to readjust for our concentrations. So we now divide by our total volume of 15 milliliters added, as well as our 16.8 milliliters of base. Our concentration of the hypochlorite ion and the hypochlorous acid are equal. When we go to solve our equilibrium, we use those concentration values at the end of that stoichiometry problem with the weak acid, strong base, our change, and our final concentrations at equilibrium. Now, because the concentrations of the hypochlorite ion and the hypochlorous acid are equal, we recognize that this is a half equivalence, and the pH will equal pKa. Now, I'm going to go ahead and show the equations that we would use to solve the equilibrium expression for this. But keep in mind, we could find the pH by simply taking the negative log of the Ka value. If we were to plug in and solve the equation, you will see here why pH is going to equal pKa. Our equilibrium expression, 2.9 times 10 to the negative 8th, is going to approximately equal 0.132x divided by 0.132. The 0.132's cancel out, leaving us with x equaling our Ka value. That Ka value is equal then also to the hydronium ion concentration. Notice again that our hypochlorite ion has not changed in concentration because the x value is too small. Our pH then is simply going to be the negative log of the value for x, and that value for x was our Ka value. So if we were to take the negative log of our Ka, we would come up with the pH of 7.54. If we continue on, we're still going to have an excess of acid, but we are narrowing it down. We're getting closer to the point where we are getting equal numbers of moles of acid and base. So we've gone through this once before. We're going to have the neutralization reaction because the reaction is going to go to completion. We're going to set up a Rice table in units of moles or millimoles. We're going to identify the weak acids and bases and then recalculate the concentrations with the new volumes. We'll then go to our weak acid equilibrium and go through the process of setting up the Rice table, calculating our equilibrium values, and determining what our pH and pOH are based on those equilibrium values. So if we look at our next addition, we're going to have our weak acid strong base reaction going to completion where we have 8.40 millimoles of hypochlorous acid. This time around we have 7 millimoles of hydroxide, still less than the number of moles of hypochlorous acid, but increasing. We also are starting off again with 0 millimoles of hypochlorite ion. Our change is going to be 7 millimoles because all of the hydroxide will be used, and we will be left with our excess of hypochlorous acid of 1.4 millimoles, and we will produce 7 millimoles of hypochlorite ion. Those values then are used to recalculate the new concentration based on the new volume. Those concentrations then are going to be used in our Rice table for our equilibrium of the weak acid. So we're going to start off with 0.0326 hypochlorous acid and 0.163 molar hypochlorite ion. We get our changes and we get our equilibrium values. Those values then are plugged into our equilibrium expression. Again, we make our assumption and we calculate x to be 5.8 times 10 to the negative 9th. And that will be our concentration of hydronium. Again, x is too small to really matter, so our hypochlorite ion concentration is also going to be 0.163. The pH determined from the value of x, which is the hydronium concentration, is 8.24, and the pOH is 5.76. As we continue on, we're going to eventually reach the point where the number of moles of weak acid and the number of moles of base are going to be equal. This is what we call the equivalence point. And not much changes here until we get to our equilibrium. We do the neutralization stoichiometry, Reaction goes to completion. We set up a Rice table in millimoles. We identify our weak acids and bases remaining, and we do our calculations using our new volumes. The second part of our titration calculation is going to involve the equilibrium of a weak base. Because at equivalence, the amount of acid and base are equal, we will have 0 of our weak base left over. We will have the conjugate base of that acid as a product, and that ion will be the ion determining the pH of our solution. So we need to write out a new reaction, in this case for the weak base, that's the conjugate base of the acid that we were dealing with, in water. Then we set up a Rice table, or using the concentrations from the previous neutralization stoichiometry. We determine our Kb based on what our Ka value is. We use that Kb value and the values from our Rice table to calculate our equilibrium values. And then we go through and calculate our pH and pOH. We have our strong base weak acid reaction. We initially are going to have 0.840 millimoles of hypochlorous acid. We are also going to have 8.40 millimoles of hydroxide. Because they are equal, the amounts of the weak acid and strong base left over after the stoichiometry is complete is 0. In this case, the only ion that we have available to come to an equilibrium with water is our hypochlorite ion. So we determine what its concentration is going to be, and we end up with 0.173 moles per liter of hypochlorite ion. Now, because we have only the hypochlorite ion, we need to write out our new reaction. And hypochlorite ion, being a weak base, will react with water to produce hydroxide and hypochlorous acid. In our Rice table, we start off with 0.173 molar of hypochlorite ion. We have none of the hydroxide and hypochlorous acid to begin with initially. We set up our change, and this would be our equilibrium values. Now, to set up into our equilibrium expression, we need to know what the Kb is for hypochlorite ion. And here we would use our rearranged equation for Kw equals the Ka times Kb. We know the Ka for our hypochlorous acid, so we can calculate the Kb value for the hypochlorite ion because the hypochlorite ion is the conjugate base of hypochlorous acid. We then set up our equilibrium expression. We calculate for x, and x is going to give us 2.4 times 10 to the negative 4th, and that's the concentration of hydroxide ion. It's also the concentration of our hypochlorous acid. The pOH can be determined by doing the negative log of the 2.4 times 10 to the negative 4th, and pOH is 3.62. Our pH then can be determined by using the equation 14 equals pH plus pOH. One of the things to notice here is that at equivalence, our pH is 10.38 because the salt that's produced, in this case, the salt contains the hypochlorite ion, which acts as a base in solution, raising the pH above a pH of 7. If we were to continue to add base, the base will now be in the excess. And the process of going through and calculating the pH of these solutions, again, is going to be pretty much the same. We do the reaction, it's going to go to completion. We use the Rice table to find out how many millimoles of reactants and products are going to be formed and left over. We're going to recalculate those concentrations based on the new volume. Now, because the hydroxide ion is going to be the excess, our pH and pOH is going to determine solely on the hydroxide ion concentration. Now I'm going to go through and show the equilibrium process of this and why we really don't need to do it. So in our reaction, we have our hypochlorous acid reacting with excess base, producing water and hypochlorite ion. Our initial values are going to be that we start off with 8.40 millimoles of hypochlorous acid. We have 8.75 millimoles of hydroxide and nothing for our hypochlorite ion. Our change is going to be 8.40 millimoles. Now this is because the hypochlorous acid now is our limiting reactant. We have more moles of hydroxide. So at equilibrium, we will have 0.35 millimoles of hydroxide ions and 8.40 millimoles of hypochlorite. When we recalculate for our concentrations, we will end up with 0.00700 moles per liter of hydroxide and 0.168 moles per liter of hypochlorite ion. Now technically, we could stop here, find out what the pOH is, determine the pH, and other concentrations based on the hydroxide ion only. But let's see why. If we go through and start our equilibrium, we have our hypochlorite ion, concentration of 0.168. We have hydroxide ion present already. Our change, and at equilibrium, these would be our values. If we plug into our equilibrium expression for the base, we would end up with X equaling 8.2 times 10 to the negative sixth. Now, notice that our concentration of hydroxide is not going to change based on this reaction. The amount of hydroxide produced by this equilibrium reaction is not going to change the concentration of hydroxide already present initially. That's why we could go through and actually do our calculation without doing the equilibrium for pOH. The pOH would be based on that 0.007 moles per liter of hydroxide and would end up being 2.15. Our pH for this solution would be 11.85. So once you've reached a point in a titration where the strong base is in excess, the pH of the solution will be determined by what the concentration of the hydroxide ion is from the excess. So let's go through and summarize what you're going to do. Prior to any addition of sodium hydroxide, the pH and the concentrations of all the ions in solutions is going to be determined by the weak acid only and its equilibrium with water. After the addition of some sodium hydroxide, and prior to the equivalence point, you will have excess acid, and you will do two parts. You'll do a neutralization stoichiometry problem, and then you will set up an equilibrium expression based on our concentrations after the neutralization reaction has taken place. At 1/2 equivalence, you recognize this when you do your stoichiometry and see that the number of moles of strong base is 1/2 the number of moles of weak acid. At this point, the pH will equal the pKa. If you continue to add base, but the acid is still in excess, just as we saw in number 2, you do two parts. You do a neutralization reaction between the acid and base, and then you set up an equilibrium based on the concentrations from that neutralization reaction. When you reach the equivalence point, the pH of the solution and pOH is going to be determined by the conjugate base. You no longer have any weak acid left. The only ion that's going to be involved in causing the solution to have a pH is going to be the conjugate base. Continued addition of strong base will make it the excess. You'll have a neutralization reaction, but you will have strong base or hydroxide ions left over. And those hydroxide ions will be used to do the calculation for pH and pOH. The conjugate base that is produced in the neutralization reaction will contribute very little hydroxide ions compared to the amount of hydroxide that's going to be in excess.